Okay, guys, today we're going to be looking at where electrons go in atoms using orbital notation. So as you may already know, in an atom, electrons reside in specific orbits. And these orbits, they look like circles on paper. In reality, they're three-dimensional and they're a little bit more complicated. And they have energy levels and suborbitals. And today we're going to be looking at exactly how that works. So here on the screen in front of you is what looks like a random assortment of boxes. And it may seem that way, but they are in fact not quite random. So if you have seen the electron configuration video, you know that electrons fill the levels in a specific order. And if you did the electron configuration, you know the pattern goes like 1s2, 2s2, 2p6, 3s2, so on and so forth. And that's the same pattern we're going to be following here with the orbital notations. We just have some boxes laid out for us. So we're going to look at some elements and see where their electrons go on this diagram. The first one I'm going to look at is going to be hydrogen. So hydrogen has an atomic number of one proton, which means that in its regular ground state, it only has one electron. So its lonely electron needs to find somewhere to live in this diagram of orbitals. So there's three different laws that we're going to be looking at. The first one is called Aufbau's principle. So Aufbau's principle, which can be found in the key terms of your digital notebook, but Aufbau's principle states that electrons fill the lowest energy orbital first. Notice that I said orbital and not level, and we'll see why that is here in a second. So according to the Aufbau principle, hydrogen's one electron is going to reside inside the lowest level box, which down here is the 1s. So we're going to represent electrons as little arrows, and that's because they have a thing called spin up and spin down. We'll talk about that here in a second. But that first electron, and hydrogen's only electron, fills the lowest box first. And you can see that the electron configuration is going to come from this because the electron configuration for hydrogen is just 1s, and there's only one electron in that box, so it's 1s1. Now, if we move up an element, say let's do helium. Now, helium has two electrons. Its atomic number is 2. In its ground state, electrons have to balance protons. So we're going to have to add some additional rules for how to fill these. According to the Aufbau principle, we're going to start on the lowest level. In order to fill the second electron in, we have to know something called the Pauli exclusion principle. Pauli exclusion principle. And the Pauli exclusion principle basically says that only 2 electrons can go in each of these boxes. So we've got all these boxes. Only 2 electrons can go in each one, and they have to have opposite spins. One will be spin up, the other one will be spin down. So electrons are going to fill the lowest energy level, the lowest energy orbit, but they can only fit 2 in a box, and one has to be up and the other has to be down. So helium's 2 electrons will both be in the 1s, one will be up, one will be down. So helium's electron configuration is 1s with 2 electrons in the 1s, 1s2. All right, now for some practice, let's do lithium. Lithium has 3 electrons. So we fill in the first 2, just like we did with helium. But there's no more room for the third one. So the third one jumps up a level to 2s right there. So the electron configuration for that is 1s2, because we got 2 electrons in the 1s. And then in 2s, we only have 1 electron. So it goes 1s2, 2s1. Now, if we move on to beryllium, which has 4 electrons, we just have to add 1 more. And Pauli exclusion and off-Bow's principle state that the next one is going to go still in this lowest available position, but it's got to be spin down, which is the opposite of the first electron we put there. So this one has a configuration of 1s2, 2s with 2, because now there's 2s electrons in there. Now we're going to skip over a couple and talk about the next rule that you need to know. The next rule that you need to know is going to come up when we do carbon. So carbon has 6 protons and therefore also 6 electrons in its ground state. So let's just go ahead and start filling those in according to the off-Bow principle and the Pauli exclusion principle. We start with the lowest level, and we'll put 2 electrons in there because we can fit 2 electrons per box. One is spin up, the other is spin down. We move up to the next orbital, 2s. We can put in 1 up electron, 1 down electron, and then those are full. Then we have to move to the 2p. Now 2p is very spacious. It's got 3 boxes in it. And we've got 2 more electrons to place. So we'll put 1 there in the first box. But according to Hund's rule, this is a new one, Hund's rule, the electrons are going to spread out in those boxes before they pair up. And they can do this because they're on the same energy level, the same orbit. So it's not going to be violating the off-Bow principle for them to spread out. So my second electron that goes in the P is going to scoot over to the next box. That's because electrons like to spread out because they're both negative and negative things repel. So that would be the orbital notation for carbon. If we're going to write the electron configuration for that, it's still 1s2, because we've got 1s with 2 electrons in there, 2s2, 2s with 2 electrons in there, and 2p2, because there's 2 electrons in the 2p. All right, so we're going to skip pretty far ahead in the elements to something that is going to be a little bit more challenging, and that's going to go all the way to, let's say, bromine, which is element number 35. That's a lot of electrons to do. Okay, so we're going to start filling them up according to our 3 rules. Start at the bottom. We can put 2 electrons in each box going opposite spins. So there's 1, 2, move up to the next one, 3, 4. Electrons are going to spread out in the P. So 5, 6, 7. But then they have to go back in and fill the rest of the energy level, 8, 9, 10. Moving up to the 3s, 11, 12. Then over to the 3p, 13, 14, 15. Notice they still spread out. And then fill back in, 16, 17, 18. Moving up to the 4s, 19, 20. And then we get to this thing that's 3D, which is a little bit weird. And it's because you would assume that the 3D would come under the 4s because it's got the 3. That must mean it's on the 3rd energy level. And because of the way the Schrodinger equation works and quantum mechanics and all sorts of crazy stuff that's beyond the scope of this class, the 3D actually holds higher energy values than the 4s. So it comes above the 4s, but it has lower energy values than the 4p. So it goes between 4s and 4p. So it gets filled in after the 4s. I know it's weird, but you're just going to have to accept it or, major in chemistry or physics. But we were at 20 electrons, so we're going to fill in the 3D. And they're still going to spread out in there. So that's 21, 22, 23, 24, 25. And then we got to fill back in 26, 27, 28, 29, 30. Moving up to 4P, 31, spread out 32, 33, 34, 35. So that would be the orbital notation for bromine. If you wanted to write the electron configuration from that, you'd start with 1s. So it'd be 1s with 2 electrons, 2s with 2 electrons, 2p with 6 electrons, 3s with 2, 3p with 6, 4s with 2, 3d with 10, and 4p with 5, which is the same electron configuration that you would get if you just used the periodic table and your knowledge of its properties. But there are a couple more important things to note here. One is that it would take forever to draw this diagram for an element, especially if the element has a lot of electrons. So there is a little bit of a shortcut. And that shortcut is based on the noble gases. So you learned about noble gas notation with electron configurations. And with orbital notation, it's kind of similar. At the end of every set of p orbitals, that indicates the end of a period, which is where noble gas is. And the exception for that, of course, is 1s, because helium is the second 1s. So if you stopped drawing arrows at this split, at the 1s, that's up to where helium was in the diagram. If you stop here with the 2p6, that is where neon ended. And if you stop at 3p6, that would be where argon ended. If you stop at 4p6, that is where krypton ends. And so on and so forth. 5p is xenon. You get the picture. You can figure that out. So if you need to write the orbital notation, you can do so in an abbreviated manner by just starting with a certain noble gas. So for example, if we were still doing bromine, which is the one that's still on my chart, if we were doing bromine, you could say, assume I've drawn in all the things up to argon by writing argon in brackets, and then you don't have to worry about any of this stuff down here. You don't have to do it because it's all covered with this argon, because argon has all of those electrons. You only have to do the ones that come after argon. So the way you would draw that is you'd put your symbol for argon, and then you put a box and label it 4s. Put your 2 electrons in, just like you have here. And then after 4s, you had 3d, and you'd fill out all of your 3d orbitals. I'm going to have to move these things over so I have a little bit more space. There we go. So you draw your 3d next to your 4s. I'm going to try to condense it so I have enough space, and you have to have 1, 2, 3, 4, 5 boxes in there because the 3d has 5 suborbitals in there. So you label that 3d, you draw all of your electrons in, spreading out at first, filling back in with down arrows. Sorry, mine's kind of messy. And then you've got your 4p that has 3 boxes in it, 4p. And you fill in 1, 2, 3, 4, 5 of those. So this is the abbreviated or noble gas version of the orbital notation, where you just start with a noble gas and only write the orbitals that come after that. All right, the other thing you need to be able to pull off of an orbital notation is the number of valence electrons. And valence electrons are just those that reside on the outermost shell, which is the highest coefficient number that you have. So what you'll do is you'll look at the top levels of your orbital notation. So I'll just use this one for bromine as an example. The top level here is 4. 4 is the highest number achieved. So we'll look at the number of electrons that reside on the 4th energy level. And the number of electrons there is the number that's in S plus the number that's in P. So we've got 1, 2, 3, 4, 5, 6, 7 valence electrons in the S and P. This d orbital does not count because it is on level 3. And you'll see if you practice these enough that the d orbital actually never counts in valence electrons because by the time you get to filling up the d orbital, you've already filled in the higher level's s orbital. So the maximum number of valence electrons that an atom can have is s plus p, which is a total of 8. So you can never have more than 8 valence electrons, even though you can have more electrons than that in a shell. Hopefully this was helpful to you. If you're still confused, please let me know, or please let Ms. Rigsby know. We'll try to help you out best we can. But you do have to know how to do this stuff for pre-AP.